Today we will study Boolean algebra. Actually, Boolean algebra was originally introduced by British mathematician George Boole. This mathematics is an algebraic structure which is based on the principle of logics. George Boole published a research paper named Law of Thoughts in which he described that different fundamental principles of logics can be expressed by symbolic notations. Suppose B is any set of numbers or sets or objects or statements or switches, and in B2 binary operation, union and intersection or join or meet or plus means addition and multiplication are defined. Then the algebraic structure B union intersection or B join meet or B together with addition and multiplication is called a Boolean algebra if it obeys certain laws. The identity elements for the two operation union and intersection are respectively empty set and the universal set 1, and for operation join and meet are 0 and 1. Sometimes 0 also refers to the statement which is false and 1 refers to the statement which is true. And the operations addition and multiplication, and for addition the identity element is 0 and for multiplication the identity element is 1. Now we formally define the Boolean algebra. Let B be a non-empty set with two binary operation join and meet. Then the algebraic structure B join and meet is called Boolean algebra if the following axioms hold. Number 1, closure property, which means A join B as well as B meet A, or it may be A meet B belongs to B. Second, commutative law hold, means A join B is equal to B join A and A meet B is equal to B meet A for all AB belonging to B. Distributive law hold, means A join B meet C is equal to A join B meet A join C. A meet B join C is equal to A meet B join A meet C. Next, there exists an identity element. Identity elements, in fact, there exist two identity elements, phi with respect to join and I with respect to meet, so that A join phi is equal to A meet I equal to A. If the operation is addition and multiplication, we can also write it as 1 and 0. Complement laws means A join A is equal to I, A meet A dash equal to phi. And last one is both the identities are not equal, means phi is not equal to I. These identity elements depend on the relation and the set under consideration. Clearly, Boolean algebra consists of at least two elements, which are two identity elements with respect to two binary operations. Now we will consider one example. Let B be the set of all positive divisors of 30. We know that divisor of 30s are 1, 2, 3, 5, 6, 10, 15 and 30. These are all divisors of 30. And the operations are meet and join on B, where A join B means LCM of A and B and A meet B means HCF of A and B. Then this set B together with the operation join and meet, which are defined like this, means A join B is LCM of AB, A meet B is HC of AB, is a Boolean algebra. To prove that this is a Boolean algebra, first of all we construct composition table with respect to the two operations join and meet. We write the elements of B in top border row and extreme left column. We write the elements in the top border row and extreme left column. Then we know that because join means LCM of AB. LCM of 1 and 1 is 1, LCM of 1 and 2 is 2, LCM of 1 and 3 and 3, and so on. Then LCM of 2 and 1 is 2, LCM of 2 and 2 is 2, LCM of 2 and 3 is 6, LCM of 2 and 5 is 10, LCM of 2 and 6 is 6, LCM of 2 and 10 is 10, and so on. LCM of 3 and 1 is 3, LCM of 3 and 2 is 6, LCM of 3 and 3 is 3, LCM of 3 and 5 is 15, LCM of 3 and 6 is 6, LCM of 3 and 10 is 30, and so on. So similarly, we complete table for all the elements of B. Then in case of meet means A meet B means HCF of AB. HCF of 1 and 1 is 1, HCF of 1 and 2 is 1, HCF of 1 and 3 is 1, HCF of 1 and 5 is 1, HCF of 1 and 6 is 1, HCF of 1 and 10 is 1, and so on. HCF of 2 and 1 is 1, HCF of 2 and 2 is 2, HCF of 2 and 3 is 1, HCF of 2 and 5 is 1, HCF of 2 and 6 is 2, HCF of 2 and 10 is 2, and so on. HCF of 3 and 1 is 1, HCF of 3 and 2 is 1, HCF of 3 and 3 is 3, HCF of 3 and 5 is 1, HCF of 3 and 6 is 3, HCF of 3 and 10 is 1, HCF of 3 and 15 is 3, HCF of 3 and 30 is 3, and so on. So we complete these two composition tables with respect to the operations A join B, join and meet. We notice from these tables that all these elements in this table and all these elements in these tables belong to this set. Number 2, if this is the main diagonal, then we notice that all the elements around this main diagonal are symmetrical. Means here we have 2, 3, 5, 6, 10, 15, 30. Here also we have 2, 3, 5, 6, 10, 15, 30. Here we have 2, 6, 10, 6, 10, 30, 30. Here also we have 2, 6, 10, 6, 10, 30, 30. Here we have 3, 15, 6, 30, 15, 30. Here also we have 3, 15, 6, 30, 15, 60, 30. So all the elements are symmetrical about the main diagonal. See, here it is 30, 30. This is also 30, 30. This is 30, this is 30. Here also all the elements are symmetrical about the main diagonal. Means here it is all ones. Here it is 1, 1, 2, 2, 1, 2, 1, 1, 2, 2, 1, 1. Here also 1, 3, 1, 3, 3. So it is 1, 3, 1, 3, 3. Here it is 1, 5, 5, 5. Here it is 1, 5, 5, 5. So all the elements about the main diagonal are symmetric. So all the elements of this set belong to the set, means closure property is satisfied. And all the elements are symmetrical about the main diagonal, means commutative law holds. Now we construct one more composition table for complement. Complement of 1 is 30, complement of 2 is 15, complement of 3 is 10, complement of 5 is 6, complement of 6 is 5, complement of 10 is 3, complement of 15 is 2, complement of 30 is 1. Now, because all the elements of both the composition table belongs to B, hence B satisfies closure property. Since the elements are symmetrical about the main diagonal of the composition tables, closure law holds. Means A join B is equal to B join A, and A meet B equal to B not A. Also, we can verify from the composition table that A join B meet C is equal to A join B meet A join C. This can be verified from the composition table, and A meet B join C is equal to A meet B join A meet C. Clearly, identity element with respect to join is 1, and identity element with respect to meet is 30. This is the identity element with respect to meet, because this row is identical with the top border row. So element on its extreme left is the identity element, and in this case first row is identical with the top border row, and element on the extreme left is the identity element. This is the way how we check the identity elements. We need to check which two rows are identical. First row is identical with the top border row, so element on its extreme left, 1 is the identity element. Here this last row is identical with the top border row, therefore element on its extreme left, 30, is the identity element. Complementation: for each A belonging to B, there exists its complementary element B such that A join B equal to 30 and A meet B equal to 1. Clearly, both the identity elements are distinct. Now, we consider one more example. To show that the structure B plus dot, this is addition multiplication, is a Boolean algebra for B equal to 0, 1 with operation addition and multiplication, and this complement is a unary operation on B. And plus dot is missing here. Plus and dot are two binary operation on this set. First of all, we construct the composition table. We have only two elements, 0 and 1. We write in the top border row, and this side 0 and 1. This is 0 and 1, this is 0 and 1. With respect to addition, 0 plus 0 is 1, 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1. Means it is not ordinary addition. 0 dot 0 is 0, 0 dot 1 is 1, 1 dot 0 is 0, 1 dot 1 is 1. Complement of 0 is 1, complement of 1 is 0. Here also all the elements belong to this set, therefore closure property is satisfied. Here also elements are symmetrical about the main diagonal. This is the main diagonal, here also we have 1 and 1. This is the main diagonal, here we have 0 and here also we have the 0. Therefore commutative law holds. Also 0 plus 1 is equal to 1 plus 0 equal to 1, 0 into 1 is equal to 0 equal to 1 into 0. Hence both the operations plus and dot are commutative. Now this row is identical with this row, so element on its extreme left 0 is the identity element with respect to addition. Now this row is identical with this row, so element on its extreme left 1 is the identity element with respect to dot. Also we can check that 0 plus 0 is 0, 1 plus 0 is 1, 0 into 1 is 1 into 0 equal to 0, 1 into 1 is 1. So 0 is the additive identity and 1 is the multiplicative identity. Also we can check that distributive law holds. Because 0 plus 1 into 0, we know that 1 into 0, 1 dot 0 is 0. So 0 plus 0 equal to 0. 0 plus 0 is 0. Also 0 plus 1. 0 plus 1 is 1. And 0 plus 0. 0 plus 0 is 0. And 1 into 0. 1 into 0 is 0. So this is 0. So these two are equal. Means 0 plus 1 into 0 is equal to 0 plus 1 into 0 plus 0. Therefore every operation plus and dot is distributive over other operation. Clearly complement of 0 is 1 and complement of 1 is 0. Hence the complement of each element A belonging to B exists. It means B plus dot is a Boolean algebra. Here this bracket is before B, like this. B plus dot is a Boolean algebra. Now the idempotent law. Idempotent law states that for every element of a Boolean algebra B, A plus A is A and A dot A is A. Now we will prove this idempotent law. For the first case, in the left hand side we have A plus A. We can write it as A plus A dot 1. Because of the existence of identity element, we know that A dot 1 is equal to A. And 1 can be written as A plus A dash. By complementary law, A plus A dash is 1. So this can be written as A plus A dot A dash by distributive law. But A dot A dash is 0 by complementary law. So A plus 0. And by existence of identity element, A plus 0 is A. So this is A, this is equal to right hand side. So A plus A is equal to A. Now for the second idempotent law, in the left hand side we have A dot A. We can write A dot A plus 0. Means existence of identity element A plus 0 equal to A. So this 0. By complementary law, A dot A dash is 0. So we can write it A dot A dash. So this can be written as A dot A plus A dash by distributive law. But A plus A dash is 1 by complementary law. So A dot 1. And this is A, existence of identity element A dot 1 equal to A, and this is right hand side. So we have proved the idempotent law, according to which A plus A equal to A dot A equal to A for every element of a Boolean algebra B. Second is absorption law. For any two elements of a Boolean algebra B, A plus A dot B equal to A dot A plus B equal to A. For the first part, let us consider the left hand side A plus A dot B. We can write it as A can be written as A dot 1 plus A dot B because identity element exists and multiplicative identity is 1. A dot 1 is 1. So by distributive law, A dot 1 plus B equal to, this is by distributive law, and 1 plus B is 1. So A dot 1 is A. So in the right hand side, this is equal to right hand side. So by absorption law, A plus A dot B equal to A. Now for the second absorption law, left hand side is A dot A plus B, A plus 0 plus A plus B. It is equal to A plus 0 into B by distributive law. This is why existence of identity. A can be written as A plus 0. And by distributive law, A plus 0 into B. As 0 into B is 0, so A plus 0 is A by existence of identity element. So this is equal to right hand side. So it means A dot A plus B equal to A. One more theorem. In a Boolean algebra B, the identity elements are complementary to each other. Means complement of 0 is 1 and complement of 1 is 0. Here in the left hand side we have 0 dash. 0 dash means complement of 0. So we can write 0 dash as 0 dash plus 0 because existence of identity 0 dash plus 0 is equal to 0 dash is A plus 0 is A. And this can be written as 1. 0 dash plus 0 is 1 because by complementary law A dash plus A is equal to 1, and this is the right hand side. For the second part, complement of 1. This can be written as complement of 1 into 1 because existence of identity element implies A dot 1 is A. And this is equal to 0 because by complementary law A dash dot A equal to 0, and this is right hand side. So we have proved that in Boolean algebra, the identity elements are complementary to each other. Means 0 dash is complement of 0 is 1 and complement of 1 is 0. Now we will prove that the identity elements in a Boolean algebra are unique. Means we cannot have more than one identity elements. Now first of all we prove that the identity element 0 is unique for addition. Suppose we have more than two identity elements 0 and 0, 1. If 0 is the identity element, then it means 0, 1 plus 0 is 0, 1. Because 0, 1 is the identity element, 0 plus 0, 1 is 0. Since addition is commutative, therefore 0, 1 plus 0 is equal to 0 plus 0, 1 implies 0, 1 is equal to 0. Hence the identity element 0 is unique. Now we will prove that identity element 1 is unique for the operation multiplication. Suppose we have more than one identity element and one identity element is 1, another is 1, 1. If 1 is the identity element, it means 1, 1 into 1 is 1, 1. If 1, 1 is the identity element, it means 1 dot 1, 1 is 1. Since the operation is commutative, therefore 1, 1 dot 1 equal to 1 dot 1, 1 is, and this implies 1, 1 equal to 1. Hence the identity element is unique. Now we will show that complement of each element of Boolean algebra is unique. We cannot have two complements for any element of the Boolean algebra. Suppose A belongs to B be any element and X and Y be two complements of A. Then by definition we have A plus X is equal to X plus A equal to 1 and A dot X equal to X dot A equal to 0. Because y is also complement of A, so A plus y equal to y plus A equal to 1 and A dot y equal to y dot A equal to 0. Now x is equal to x dot 1. Existence of identity a dot 1 equal to a. And this is equal to x into a plus y, because a plus y is 1. And this is x dot a plus x dot y by distributive law. And x dot a is 0. So this is 0 plus xy. And this is equal to 0 can be written as a into y, because 0 is a into y. Here this can be written as a plus x into y by distributive law, but a plus x is 1 by this. So 1 into y and 1 into y is y. Hence it shows that complement of each element is unique. We cannot have two complements for any element. If we suppose two elements, then these two complements will be equal. Means complement is always unique. Thank you.